Welcome back. So I'm going to continue the discussion talking about sp2 and sp3 hybridization. So next example is going to be this. It's going to be AB3. Okay. And example we can introduce it will be BF3. So we have 1 boron plus 3 fluorines. Boron is a group 3, fluorine group 7, or it has 7 valence electrons. So I go 1 multiply 3 electrons plus 3 multiply 7. That's going to give me 24 electrons. Electronegativity of fluorine higher than electronegativity of boron. What does it mean? It means boron is the central atom. Okay, so boron is the central atom. Here you go. We have 3 fluorines. Let's show the fluorines. Okay, we put 1 fluorine here, second there, and the third one, let's put it here. Let's bring this one is a bit closer. Same thing there. Okay, and we're gonna now attach them. Okay, so 1 bond, 2, and that's gonna be the third bond. Okay, so out of 24, we use 6. Now we are plus 18. Okay, what do I do with the 18? Okay, I draw a circle around each outer atom. I can do it also with the central atom, but for now, let's just zoom on outer atoms. Okay, so the outer atoms, we need to give them 6 electrons. So I'm going to give each one 6 electrons and repeat this one 3 times. So minus 6 electrons, and I'm going to repeat this one 3 times because I have 3 fluorines. Okay, so now I'm 0. Okay, fluorine has 7 electrons, made 1 sigma bond, so it will be 8. Okay, 7 plus 1, 8. And here, 7 plus 1, 8. How about the formal charge? If you check the formal charge for any fluorine, fluorine is a group 7. How many electrons inside the circle do we see? Okay, I see 7 inside the circle, so minus 7, it will be 0. So the formal charge, 0, 0, and here also is 0. Okay, how about our central atom? Okay, the central atom, if you draw a circle around it, you see you have only 3 electrons inside the circle. So I go 3 plus 3 sigma bond, it will be 6. It's not active. How about the formal charge for it? The formal charge is a group 3. Boron is a group 3 minus. I see 3 electrons around it, so it will be 0. Okay, let's highlight the formal charges, 0, 0, 0. And that one also 0. Okay, yes, our central atom is not active, but all the formal charges are equal to 0. Do you want to share 1 lone pair from fluorine with boron? Do it. You can do it, but it's going to cost you something. And let me show you what's going to be the cost for it. Okay. So if I share 1 lone pair from one of the fluorine, it doesn't matter which fluorine. Let's go after the top one. Okay. So I'm going to share 1 lone pair from fluorine with the central atom. So that lone pair is gone. And now I have a pi bond. I have a double bond here. Okay, I'm going to show it here. I have a double bond. Okay, so what will happen with the fluorine? Fluorine, I see 6 electrons here. We made 2 bonds. It will be 8. It's active. That's fine. How about the formal charge? Fluorine is a group 7. But I see only 6 electrons around it. So it will be plus 1. And this is the issue. Remember, electronegativity of fluorine is higher than electronegativity of boron. So if there is a negative charge, it should be on fluorine, not boron. How about the boron? Boron, I see 4 electrons there. We made 4 bonds, so it will be 8. It's happy. Now it's active. Used to be 6, now turned to 8. That's good. But here, there was like issue there. Okay, how about the charge? When we check the charge, boron is a group 3, and I see 4 electrons around it, so it's minus 1. Okay, what happened? The charge now is minus 1. Okay, -1. Negative charge is on the most electropositive element, not fluorine. And that's the issue, okay? This is the issue. So the second Lewis structure, and second Lewis structure, everything is active, that's good, but you put the positive charge on the most electronegative element, and negative charge on the central atom. It should be opposite. Number one, everything, all the formal charges are 0, but your central atom is not active. How do I know which one is the dominant? You go and you measure the bond length. If the bond length is around single bond, then number 1 is the dominant. But if the bond length is a bit shorter than a single bond, because 1/3 of the time at least, or 1/4 of the time, okay, 1/4 of the time, that can be double. If it's a double, that means maybe second Lewis structure is the correct Lewis structure. Okay. And okay, let's go talk about the hybridization. Okay. So again, it doesn't matter which Lewis structure you pick. So for example, if I pick this, okay, I'm going to say I have 3 sigma bonds for central atom and 0 lone pair. Sigma plus lone pair, I got it equal to 3. Expected geometry, okay, I have 1, 2, 3. I see 3 of them, so I will call it trigonal or trigonal, because I see 3 of them, 1, 2, 3, trigonal or trigonal. And is it flat? Yes, it's completely planar, and the bond angle between them is 120. Okay, the bond angle here is 120. So it's completely flat and is 120. So I'm going to call it trigonal planar. Okay. Again, we have 3, okay, because we got 3 pairs. So we're going to use 1 from S, but this time 2 from P, and the hybridization is going to be this. We get 3 orbitals of S1 and P2. Okay, let's show them in the central atom. Okay, our boron has 3 hybrid orbital. Okay, you can say this is the first one, that's going to be the second, and the third one is here, because you want to get the maximum bond angle between them. Okay, each of this is a sp2 orbital. Boron is a group 3, or it has 3 valence electrons. Okay, 3 valence electrons. I'm going to show the valence electron. 1, 2, 3. Now let's show the fluorines. The fluorine are going to reach from this side. Fluorine will show up with opposite spin. Okay, and that's going to give me 3 sigma bonds. Okay. And what's the bond angle between them? Expected bond angle. I'm going to say the expected bond angle with red. Theta will be 120 degrees. Okay, so next one, we're going to switch to AB3. AB3, wait, AB4, forgive me. AB4. Okay. And example, you can go with CF4 or CLF4. And then, yeah, CF4 or CCl4. Okay, so I go 1 carbon plus 4 fluorine. 1 multiply 4 plus 4 multiply 7. I get 32 electrons. Carbon is the central atom because it has less electronegativity than fluorine. Okay, carbon is the central atom. I go 1 fluorine, 2, 3, and that's going to be the fourth one. So out of 32, I used 80 electrons plus, okay, 24 electrons. What do I do with them? I'm going to give each fluorine 6 electrons. Repeat this one 4 times. Okay, so now if you check fluorine, any fluorine or any carbon, or any fluorine or carbon, you will find them that they are acted. So for fluorine, I see 7 electrons. We made 1 sigma bond is 8. And how about the formal charge? Fluorine is a group 7, and I see 7 electrons around it. So the formal charge is 0. Okay, the formal charge for all fluorines will be equal to 0. How about carbon? Carbon, okay, I see 4 electrons inside the circle. We made 4 bonds. It will be 8. Carbon is a group 4. How many electrons inside the circle do we see? We see 4 of them. So the formal charge, again, it will be 0. And if you add all the formal charges, the answer is going to be equal to 0. Okay, why? Because CF4 has no charge. That means the charge is equal to 0. Okay, so no charge means charge is equal to 0. Okay, I got 4 sigma, 4 sigma, and 0 lone pair on the central atom. Sigma plus lone pair, it will be 4 expected geometry. Will be tetrahedral. But how about the hybridization? I have 4 pairs. That means I have 8 electrons. Okay, 4 pairs. So we're going to use 1 from S and 3 from P, and that's going to give us 4 orbitals of S and P. And what's the hybridization? From S, we used 1. From P, we use 3 of them. Okay, I should say this. This 1 does not mean N is equal to 1. That's not correct. And that's 3 does not mean N is equal to 3. Okay, those are just simply showing you a number of orbitals. How many p orbitals did you use? I used 3 of them, and from S I use only 1. Okay, that's the meaning of, not 1s or 3p. Okay, now let's show carbon. This is carbon, and carbon. Okay, carbon is a group 4. 4. It means it has 4 valence electrons. 1, 2, 3, 4. Okay. And when fluorine or any other atom is reaching it, it's going to reach it through those sides. So you will have fluorine here. And fluorine will come with opposite spin. Now you got 4 sigma bonds. So this is 1 sigma bond, and that's the 2nd sigma bond. Okay, here is the 3rd. That one is the 4th. So I got 4 sigma bond. Okay, now what's the bond angle between them? The bond angle between them is 109. So theta is going to be equal to 109.5 degree. Okay. So after this, I'm gonna introduce lone pair and see what's gonna be effect of lone pair on the system. Okay, so let's go with this. Okay, we go AB3, but the fourth one we're gonna use E, and what's the E? It will be lone pair. And one example, we can go with NH3 or CH3 minus 1. CH3 minus 1. Okay, so I'm going to show you both of them. For NH3, you say 1 nitrogen plus 3 hydrogen. So you go 1 multiply 5 because nitrogen is group 5. 3 multiply 1 for hydrogen, so you get 8 electrons. For CH3 minus 1, you will say 1 carbon plus 3 hydrogen minus charge. Minus of the charge. So you go 1 multiply 4 for carbon plus 3 multiply 1 for hydrogen minus of the charge. And what's the charge? Charge is minus 1. Okay, your charge is minus 1. Remember, we are saying minus of the charge. So it will be minus of minus 1. And that's going to give you 8 electrons. Okay. 8 electrons. So let's go with CH3 minus 1 first, and then, okay, then we're going to get, you know, like we're going to show the NH3. Okay. So I have carbon, 3 hydrogens around it. Attach them. Okay. Hydrogen can have only 2 electrons and is already full. So hydrogen cannot accept more electron. In total, we had 8. And we use 6 of them. So we made 3 sigma bonds. What do I do with the rest of the electrons? I have no option other than showing them on the central atom. So I put them as a lone pair. Lone pair we show here, just simply 2 dots top of the central atom. That means you have a lone pair on carbon. Okay, you have a lone pair. So I got 3 sigma and 1 lone pair on carbon. So sigma plus lone pair on carbon, we got it equal to 4. Okay, because this one is 4. Hybridization, again, is going to be 1s and 3 from P. You get 4s1p3. So hybridization is not going to change because you got it 4. Okay, let's show the central atom. Central atom here is attached to 3 hydrogens. And you have a lone pair here. You have a lone pair. Lone pair is going to push the bond pair down because it requires more space. Okay. And the bond angle from 109.5 for tetrahedral geometry, it will go down by 2 degrees. And what do we get? We get 107, around 107. So the expected bond angle is going to be 107. Okay, from 100. Now, what's going to be the geometry? Okay, the geometry, let's put it this way. Okay, here. What do you see? 1, 2, 3. I see 3 atoms, okay? 3 green atoms. 1, 2, 3. So I'm going to say the geometry that I see is trigonal or trigonal. Okay, I see a carbon attached to 3 hydrogen atoms. Okay, let's connect those 3 hydrogen atoms. Okay, we get a plane here. Now we have a plane. Okay, where is the lone pair? The lone pair is sitting somewhere there. That's okay. Next, we're going to attach the lone pair to the hydrogen atoms. And that's going to give us a pyramid. So if I touch this one that way, I get a pyramid. So it will be, if you attach the 3 atoms, okay, to each other, you will have a plane. I'm going to call it trigonal or trigonal. And then when I attach them to this, the top one is missing. That's a lone pair. Okay, if I attach them, I get a pyramid. So I'm going to call it trigonal pyramidal geometry. Pyramidal geometry. Okay. And again, what's the hybridization? Hybridization, it will be sp3. Okay. Now, remember, carbon is a group 4. Charge also is equal to -1. We have extra electron. We have extra electrons. So here you go. This is carbon. It has 4 orbitals attached to it, 4 hybrid orbitals. Let's show, okay, let's show the valence electrons. 1, 2, 3, 4. But we have 1 extra electron. So what do I do with it? I put it there. Now we're going to have an issue. And what's the issue? This orbital is full. And because it's full, we can use it to make a sigma bond. So that's going to be a lone pair. That's going to be a lone pair. And hydrogen atom can reach carbon only through those 3 directions. And I get 3 sigma bonds. That's going to give me 3 sigma bonds. Okay. And you have the same story when it comes to nitrogen. So for nitrogen, for NH3, so if I copy paste this one for nitrogen, another page. Okay. Let's change carbon to nitrogen. So if we change carbon to nitrogen, okay, nitrogen is a group 5. It means it has 5 valence electrons, and we're going to do the same thing here. Nitrogen has 5 valence electrons. So I put, I put the 5 electrons inside the hybrid orbitals. Those are the sp3 orbitals. Okay, and we have 4 of them. So one of the orbital remains like a lone pair, or is not going to be able to make technically a sigma bond. Okay. And so you can say geometry of CH3 minus 1 and NH3 will be the same. In both of them, they will be trigonal pyramidal. Okay. And one more example. And last example that I want to practice, it will be this. Say AB2, E2. So 2 lone pairs this time. Okay. And one example that you can use is going to be H2O, or you can say OF, for example, 2. OF2. You can say H2S. You can say SF2, for example. So I have hydrogen, 2 hydrogens plus 1 oxygen. I go 1 multiply 2 electrons. Forgive me, 2 multiply 1 electron for hydrogen, plus I go 1 multiply 6 electrons for oxygen. I get 8 electrons. Never ever put hydrogen as a central atom. You don't have an option. You go with oxygen as a central atom. So you put hydrogens around it. Okay, attach them. You got 2 sigma bonds. Okay, now let's check oxygen. Hydrogen. Hydrogen, 1 plus 1, 2, 1 plus 1, 2. Out of 8, we use 4 electrons. So now we are plus 4. What do I do with them? I'm going to put them on oxygen. And let's show oxygen. Oxygen, it will be 6 plus 2 will be 8. So oxygen now is happy. But the issue that you will have will be this. Oxygen has 2 lone pairs. Those 2 lone pairs will push the bond pair down. So they're going to push the bond pair. And the bond angle is going to shrink. Okay, so remember, right now I have 2 sigma bond and 2 lone pairs. So I expect the bond, I expect the geometry to be tetrahedral. Okay, expect it to be tetrahedral because I got 4. But in reality, the geometry is going to be this. Okay, so I used to have 4 of them. I call it tetrahedral. If I take 1, I'm not going to see the lone pair. Lone pair, we don't see it. Okay, so I say 1, 2, 3 attached to lone pair. That's going to be trigonal pyramidal. If I take the second one and I make it as a lone pair and take these 2 lone pair off, if you take them off, what do we have? Okay, what's the difference between these 2? Okay, the top one is linear. And how about this? If you take the top one and you just bend it, you bent it that way, you will get bent geometry. So the geometry is going to be bent. Okay, how about the bond angle? Perfect tetrahedral, I expect it to be 109.5. But I have 2 lone pairs, so I'm going to drop it by 4 degrees. 2 degrees per each lone pair. So we are expecting this one to be around 104.5 or 105. Okay, or you can say this one is around 105. That's a bond angle. So I expect theta to be around 104 or 105. Okay, around that number. Okay, next, how about the hybridization? Hybridization, I have 4 pairs. So I go 1 from S and 3 from P. I get 4 orbitals of S1 and P3. Okay, let's show them. We have oxygen with 4 orbitals. Okay, 4 orbitals. So here you go. I go 1 orbital here. That's the second orbital. Let's put 1 here, 4th there. Okay, or you can, really, you can just simply say 1 orbital there, 2. Okay, 2. That's going to be 3, and this one will be the 3rd one, the 4th one. Okay, oxygen has 6 valence electrons. Okay, let's show the valence electron. 1, 2, 3, 4. Okay, next 5, 6. So that means these 2 orbital will be taken, is fully occupied. And these 2 orbital will be lone pair. So these 2 orbitals are lone pair. And after atom, it can reach hydrogen, it can reach oxygen only and only through these 2 hybrid orbitals. So you put hydrogen or fluorine there with opposite spin. And that's going to give you 2 sigma bonds. And here you go. I got 2 sigma bonds. Okay, and this one is the sp3 orbital. That one as well, sp3 orbital. And okay, and this interaction, I'm going to call it sigma bond. So let me erase this one, write it somewhere else. Okay, that orbital, I'm going to call it sp3 hybrid orbital. Okay, so when you're talking about hybridization, you need to include the sigma and sigma on the central atom plus the lone pair, or sigma of the central atom plus the lone pairs that they are sitting on the central atom. Okay, and so I technically finished. Okay, I finished, this slide. So like I expect you to go through it and answer, any question that, I gave you for the class activity. Thank you very much, and I will see you soon.